The James Webb Space Telescope peers deep into the cosmos, capturing light that has traveled for more than 13 billion years. This light, stretched and shifted by the universe's expansion, reveals distant galaxies and stars as they existed shortly after the Big Bang. It's like looking back in time, witnessing the earliest chapters of our universe's history. While the universe appears infinite now, scientists believe it began from an incredibly small, dense point known as a singularity. This is the foundation of the Big Bang theory, a theory now being challenged by findings from the James Webb Space Telescope. Even renowned physicist Brian Cox has commented that these discoveries could alter how we understand the universe as a connected system. The James Webb Space Telescope, also known as JWST, is named after James E. Webb, a former NASA administrator. It represents a monumental leap in observational astronomy and was developed through collaboration between NASA, the European Space Agency, and the Canadian Space Agency. While the Hubble Space Telescope mostly observed invisible and ultraviolet light, the JWST operates in the infrared spectrum. This allows it to see through cosmic dust and observe objects that were previously hidden. By detecting infrared light, it reveals phenomena invisible to other telescopes. Launched on December 25, 2021, the JWST reached its destination at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth. There, it orbits the Sun while staying in line with Earth, keeping its instruments shielded from heat and light to remain extremely cold. This positioning is crucial for detecting faint heat signatures from distant galaxies. One of JWST's major strengths is its ability to see objects with redshift values greater than 10. Redshift occurs when light stretches as objects move away from us, and a redshift of 10 means we are seeing light from about 400 million years after the Big Bang. That's extraordinarily close to the universe's beginning, considering it is now estimated to be 13.8 billion years old. However, what scientists are finding challenges established models. JWST has discovered galaxies that appear too massive and too developed to have formed so soon after the Big Bang. Some of these galaxies have characteristics more common in mature galaxies, yet they existed just a few hundred million years after the universe began. This contradicts the standard cosmological model, which predicts that galaxies form gradually through mergers and slow accretion of matter. The telescope has also spotted galaxies that don't fit the size and brightness expectations for their time. Some are compact yet contain enormous amounts of stars. Others display rotational patterns and disk structures that, according to current theory, shouldn't exist at such an early stage in cosmic history. These findings have sparked intense debate among astronomers and physicists. Some suggest we may need to revise the standard lambda cold dark matter lambda CDM model, which has been the backbone of cosmology for decades. Others propose that dark energy, the mysterious force driving the universe's accelerated expansion, may not behave the way we thought. Even the nature of time, space, and gravity is being reconsidered in light of this new data. The telescope's ability to detect molecular signatures in distant atmospheres is also reshaping the search for extraterrestrial life. By analyzing the light that passes through the atmospheres of exoplanets, JWST can identify elements like water vapor, carbon dioxide, methane, and more. This has opened new doors in the study of potentially habitable worlds. In July 2022, JWST released its first full-color images, which included the deepest infrared image of the universe ever captured. Known as Webb's first deep field, this image shows thousands of galaxies, many of which existed when the universe was less than a billion years old. It also revealed gravitational lensing, where massive objects bend and magnify the light from more distant galaxies behind them. This helps scientists study even fainter, more distant objects. JWST has also investigated regions of active star formation like the Carina Nebula, revealing newborn stars and complex structures hidden behind cosmic dust. It has observed planetary systems like TRAPPIST-1, analyzing their atmospheres for signs of habitability. Its observations of Jupiter have shown aurorous and high-altitude hazes, while images of Neptune and Uranus have revealed their rings and atmospheric dynamics in unprecedented detail. Among the telescope's most surprising discoveries are galaxies that formed incredibly early in the universe's timeline. Some galaxies appear to have formed just 200 to 300 million years after the Big Bang. That's significantly earlier than previously believed possible. Theoretical models didn't predict such massive structures forming so soon. These galaxies challenge our understanding of how quickly matter could clump together under gravity to form stars, then galaxies. In some cases, the galaxies observed by JWST seem to rival the Milky Way in mass, yet they are observed at a time when the universe was only about 2% of its current age. There is also the matter of metallicity. Metals in astronomy refer to elements heavier than hydrogen and helium. Young galaxies were expected to have low metallicity because heavier elements are forged inside stars and accumulate over time. However, some of the galaxies JWST has discovered already contain substantial amounts of these heavier elements, suggesting a faster rate of star formation and evolution than previously thought. This rapid development hints at unknown processes or variations in early cosmic conditions. Another astonishing implication involves dark matter. According to the lambda-CDM model, dark matter forms the scaffolding for galaxies, influencing their shape and movement. But JWST has found galaxies that appear well structured and rotating smoothly without showing signs of the expected dark matter halos. This might suggest that our understanding of dark matter distribution needs revision, or perhaps dark matter behaves differently in the early universe. The same goes for dark energy. As JWST captures more precise measurements of cosmic expansion, scientists are re-examining whether the rate of expansion has been constant or changing in unexpected ways. This has implications for the ultimate fate of the universe and theories about its origin. Some physicists are even considering alternative models to the Big Bang. One such model is the bounce theory, which suggests that the universe goes through cycles of expansion and contraction, rather than starting from a singular point. Others explore the idea of an eternal inflation, where our universe is just one of many in a vast multiverse. These are highly speculative, but JWST's data may offer clues that tip the balance toward one theory or another. In the realm of exoplanets, JWST is making historic advances. It recently detected carbon dioxide in the atmosphere of a planet outside our solar system, a first in astronomical history. Such detections are key steps toward identifying planets that could support life. The telescope has also begun characterizing the atmospheres of planets in the habitable zone of their stars, seeking biosignatures, chemical signs of life. JWST's mirror, composed of 18 hexagonal segments made of beryllium and coated in gold, spans over 6.5 meters. It's the largest mirror ever launched into space. Its instruments, such as the near-infrared camera, NIR-CAM, and the mid-infrared instrument, MIRI, enable it to capture images and spectra across a wide range of wavelengths. These tools allow scientists to break down light from celestial objects and analyze its components, shedding light on the composition, temperature, motion, and age of stars and galaxies. One unexpected area of discovery involves the presence of supermassive black holes in young galaxies. According to standard theories, these enormous black holes, millions or billions of times the mass of the Sun, take billions of years to form. Yet JWST has detected quasars, the extremely luminous centers of such black holes, in the early universe. How these black holes formed so rapidly remains a mystery, prompting new theories about their growth mechanisms. Some scientists suggest they may have formed directly from collapsing gas clouds without first forming stars. Others speculate unknown processes may have accelerated their formation. These questions strike at the core of cosmology. James Webb's discoveries are not just refining our knowledge, they are forcing us to reconsider what we thought we knew. With each new image and data release, JWST is opening a new chapter in astronomy. While its mission may have begun with goals to study the early universe, its legacy may be something much greater, a complete transformation in how humanity understands the cosmos. As we continue to receive data from this remarkable observatory, the universe is no longer a distant, static backdrop. It's a dynamic, evolving realm, filled with surprises that challenge our theories and stretch our imaginations. From uncovering ancient galaxies to analyzing the atmospheres of distant worlds, the James Webb Space Telescope is revealing a cosmos more complex, more mysterious, and more beautiful than we ever imagined. And this is only the beginning.